Hello and welcome to G Fun Facts Online, the show that digs into the fascinating science behind our everyday world. Today, we're talking about something that sounds like science fiction but is very much a reality: creating a personal, miniature sun. For over a century, we've been on a quest to master the elements, to grow plants anywhere, anytime, regardless of the season or weather outside. This ambition has taken us on a remarkable journey, from the flickering glow of the first electric lamps to the sophisticated technology we have today. I am talking about full-spectrum LED grow lights. These aren't just lamps. They are marvels of engineering that can provide the precise light nourishment plants need to thrive indoors. So how did we bottle sunlight? And what makes these modern lights so different from that weird purple-pink glow you might have seen? Join me as we illuminate the science, history, and technology of the indoor sun. Our story begins way back in the late 19th century, a time of incredible electrical discovery. As early as 1861, scientists were experimenting to see if artificial light could replace sunlight for plants. Their tools were, well, let's call them rustic. They used things like open carbon arc lamps, the same tech being tested for streetlights. They were inefficient and, frankly, a bit hazardous. Fast forward to the 1920s and 30s, and Thomas Edison's incandescent bulb became the go-to tool for researchers. But these bulbs had a problem. They produced a lot of heat and a reddish light that was heavy on far-red radiation, which made plants grow tall and spindly, like they were desperately stretching for a better light source. The mid-20th century brought a big improvement with gaseous discharge lamps. Fluorescent lights became a favorite for indoor gardeners because they ran cooler, meaning you could put them closer to your plants without scorching the leaves. Then came the heavy hitters of commercial horticulture: high-intensity discharge, or HID lamps. You might have heard of their two main types: metal halide, which gives off a cooler, bluish light, and high-pressure sodium, or HPS, which casts that familiar, intense orange-yellow glow. For decades, HPS and MH lamps were the undisputed kings of indoor growing, but they were far from perfect. They devoured electricity, generated a massive amount of heat, requiring expensive cooling systems, and contained hazardous materials like mercury. The real game changer, the true revolution, arrived quietly in 1962 when a man named Nick Holonyak Jr. invented the first light-emitting diode, or LED. At first, LEDs were small, low-powered, and could only produce a single color. It wasn't until the 1990s that they really entered the horticultural world, thanks in large part to NASA. The space agency needed a super efficient way to grow food for astronauts on long missions. Their early systems used mostly red LEDs because red light is a primary driver of photosynthesis. To get the other crucial part of the spectrum, blue light, they often had to combine these red LEDs with blue fluorescent lamps. This combination of red and blue light created a very distinct purple-pink glow. The term blurple was coined to describe it, and for a while, it was the signature look of LED grow lights. While blurple lights were efficient at making plants grow, they had a downside. They made the plants look completely unnatural, making it tough for growers to spot problems like nutrient deficiencies or pests. The real leap forward came with breakthroughs in phosphor coatings. Scientists figured out that by coating a blue LED with a special mix of phosphors, they could convert some of that blue light into a broad spectrum of green, yellow, and red light. Suddenly, they could create a white light that looked much more like natural sunlight. This was huge. Not only did it make it easier for growers to actually see their plants properly, but it also opened up a new chapter in our understanding of how plants use light, revealing that they need more than just red and blue to truly flourish. So what is it about this full spectrum of light that's so important? To understand that, we need to talk about what light actually is from a plant's perspective. The light that we see is just a tiny sliver of the vast electromagnetic spectrum. For plants, the most important part is a range of wavelengths from 400 to 700 nanometers, which scientists call photosynthetically active radiation, or PAR. This is the light plants use for photosynthesis, the magical process of turning light into life. But within this PAR range, different colors have very different jobs. Let's break down the rainbow. First up, blue light. Think of blue light as the plant's personal trainer. It's a high-energy wavelength that's essential for strong, compact growth, especially when a plant is young. It drives chlorophyll production, leading to those lush, dark green leaves, and it helps develop thick stems and strong roots. Blue light also regulates the opening of stomata, the tiny pores on leaves that control the exchange of gases and water. It basically prevents plants from getting weak and leggy. Now, for years, green light was the misunderstood middle child of the light spectrum. The common thinking was, plants are green because they reflect green light, so it must not be useful. That, it turns out, is a huge misconception. While chlorophyll isn't as efficient at absorbing green light as it is red or blue, it still uses it. And green light has a superpower. It can penetrate deeper into a plant's canopy. Red and blue light get absorbed by the top leaves, but green light can filter down to the lower leaves, allowing them to photosynthesize too. This contributes to the overall health and productivity of the entire plant. Then we have the dynamic duo, red and far red light. Red light, from about 600 to 700 nanometers, is the undisputed champion of photosynthesis. It's the most efficient wavelength for converting light into energy. It's also the key signal that tells a plant when to switch from growing leaves to producing flowers and fruit. Plants have a special system of photoreceptors called phytochromes, which act like a biological light switch that is extremely sensitive to red and far red light. Far red light, which is just beyond what our eyes can see, works in tandem with red light. The ratio of red to far red light tells a plant about its environment. In nature, a plant in direct sun gets lots of red light. A plant in the shade of another, taller plant gets more far red light. This triggers a shade avoidance response, causing the plant to stretch its stem to try and outgrow its competitor and reach the sun. In a controlled indoor environment, growers can use this knowledge to manipulate plant height and encourage flowering. Finally, there's the invisible influence of ultraviolet or UV light. In large doses, UV is harmful, but in small controlled amounts, it can be beneficial. It acts as a mild stressor that kicks a plant's natural defense systems into high gear. This can trigger the production of compounds called flavonoids and terpenes, which are responsible for enhancing a plant's flavor, aroma, and even its resistance to pests. It's like a workout for the plant, making it more robust. So with this deeper understanding of the light spectrum, the technology raced ahead. The modern full-spectrum LED grow light isn't just a bulb. It's a sophisticated delivery system for a tailored diet of light. The core of it all, the LED, is a semiconductor that creates light through a process called electroluminescence. Unlike old-school bulbs that waste tons of energy creating heat, LEDs are incredibly efficient, which means lower electricity bills and a much smaller carbon footprint. This low heat output is a massive advantage. You can place the lights closer to your plants without frying them, and you don't need to spend a fortune on air conditioning and ventilation systems to keep your grow room cool. When you compare these modern marvels to the older technologies, the benefits are crystal clear. The old blurple lights are practically obsolete for serious growers now. We know that a more complete spectrum that includes green and yellow light leads to healthier plants with better structure and higher yields. And when you stack them up against the old HID kings, the HPS and MH lamps, LEDs win on almost every front. They're more energy efficient, they run cooler, they have a ridiculously long lifespan, often over 50,000 hours, meaning you're not replacing bulbs all the time. And they're safer, with no toxic mercury to worry about. The only historical downside to LEDs was their high upfront cost. But as the technology has matured, prices have plummeted. And when you factor in the long-term savings on energy and replacement bulbs, LEDs are now often the most economical choice. But if you decide to buy one, how do you choose? The first thing to know is to ignore the wattage. Wattage only tells you how much electricity the light consumes, not how much useful light it produces for your plants. You need to look at three key metrics. The first is PAR, which we already talked about. It's the type of light plants use. The second is PPF, or photosynthetic photon flux. This measures the total amount of PAR light the fixture emits every second. A higher PPF means more plant-usable light. But the most important metric for you as a grower is PPFD, or photosynthetic photon flux density. This measures how much of that useful PAR light actually lands on your plant canopy over a specific area. A good manufacturer will provide a PPFD chart showing you the light intensity at different points under the light. This is how you know if a light is truly powerful enough for your space. As a very general rule, seedlings need a lower PPFD, around 100 to 300. Plants in their vegetative growth stage need about 400 to 600. And light-hungry flowering plants like tomatoes might need 600 to 900, or even more. Many modern lights also come with amazing features like tunable spectrums, where you can literally create custom light recipes for different growth stages, or dimming capabilities and smart controls that let you manage everything from an app on your phone. So there you have it. The journey of the indoor sun has been a long one, from clunky, hazardous arc lamps to the sleek, hyper-efficient, and intelligent full-spectrum LED systems of today. We've gone from simply trying to keep a plant alive indoors to being able to provide a custom-tailored diet of light that can optimize growth, enhance flavor, and maximize yields. It's important to remember that the term full spectrum itself is more of a marketing concept than a strict scientific definition. What truly matters is that the light spectrum is engineered for the needs of plants, not just to look good to the human eye. These advancements aren't just for hobbyists growing herbs in their kitchen. This technology is at the forefront of a revolution in agriculture. It's enabling urban vertical farms to grow fresh produce in the heart of our cities, reducing food miles and increasing food security. It's helping us grow crops in regions with harsh climates, where traditional farming is impossible. The future of indoor lighting is incredibly bright. We can expect to see even more efficient lights, with artificial intelligence helping to create the perfect light recipes for any plant imaginable. By understanding and harnessing the power of light, we are not just growing plants, we are cultivating a greener, more sustainable future for everyone. Thanks for tuning in to G Fun Facts Online. Well, see you next time.